Students, Professor Nugent here. In this video, we are going to discuss a third way to demonstrate or represent the nonlinearity between the dependent variable and the independent variables. And in this case, we have multiple independent variables on the right-hand side. And in this case, we're going to see interactions between the independent variables. What do we mean by interactions? Well, perhaps a class size reduction is more effective in some circumstances than others on the test score. So the class size reduction may depend on the value of some of the independent variables. So you have some interaction effects going on between the independent variables. For instance, perhaps smaller class sizes help more if there are many English learners who need individual attention, and so you get a larger increase in the test score for a decrease in the student to teacher ratio if you have a large number of English learners, all else equal. So we're looking at the case that the change in test score given a change in the student to teacher ratio, this thing depends on the percent of English learners, hypothetically. More generally, the change in y given a change in x1 might depend on x2 or any of the included variables all the way through xk. Now, how do we model such interactions between x1 and x2? You're going to see that it is by generating a new variable. Call that, we'll just say x3, and that's going to be equal to x1 times x2. Okay? We're going to first consider the case where x1 and x2 are binary. Then we'll consider the case when one of the variables is binary and the other is continuous. And we'll conclude with the case where both x1 and x2 are continuous. Alright, let's look at the interactions between two binary variables. In this regression you see at the top of the slide with this nice big star, we have two binary variables, d1 and d2. Now beta 1 is the effect of changing dummy d1 from 0 to 1 on y. And this specification, this effect does not depend on the value of d2. To allow the effect of changing d1 to depend on d2, we need to include an interaction term. That is, we need to generate this new variable, which is the product of d1 and d2, so that the effect of a change from 0 to 1 in d1 can depend on whether d2 is also equal to 1 or not. Now the general rule here is going to... Let's look at interpreting the coefficients when we have interaction terms and both of our right-hand side variables are dummies. The general rule is to compare the various cases, and there will be 4 cases. Recall that we will have two different values for d1 and 2 different values for d2. So let's put d1 first and then d2 second. d1 can be 1 or 0. d2 can be 1 or 0. So in the first case, d1 and d2 are both equal to 1. In the second case, D1 is equal to 0 and D2 is equal to 1. In the third case, D1 is equal to 1 and D2 is equal to 0. In the fourth case, they're both equal to 0. So we want to compare all the cases. Alright, folks. If we want to focus on the effect of going from D1 equal to 0 to D1 equal to 1, then we're going to do that holding D2 constant at some value. We can hold that at some value D2. It may be 0, it may be 1. Let's call D2 in general this value D2. So then the expected value of y, given that the dummy variable 1 is equal to 0 and the dummy variable 2 is equal to D2, is equal to the intercept beta naught plus beta 2 times D2. That's this term here. The expected value of y, given that D1 is equal to 1 and D2 is equal to its value D2, is equal to beta naught plus beta 1, right, because D1 is equal to 1, plus beta 2 times D2 plus beta 3 times D2. As D2 now comes in here, and D2 comes in here, and D1 is equal to 1 here. So beta 3 comes into equation A. Now we subtract A minus B to get the change in y given the change from D1 equals 0 to D1 equals 2. And when we do that, we get this expression, beta 1 plus beta 3 times D2. So the effect of D1 depends on what is D2, which is what we wanted, right? If D2 is equal to 0, then the effect of D1 will just be beta 1. If D2 is equal to 1, then the effect of D1 will be beta 1 plus beta 3. Now beta 3, this is the increment to the effect of D1 when D2 is equal to 0. So this is that interaction effect. That extra, for instance, that extra boost of the increase in test score for lower student to teacher ratio when you have high percentage of students learning English. Let's look at this example. Define the dummy variable high STR is equal to 1 if the student to teacher ratio is greater than or equal to 20 and equal to 0 if the student to teacher ratio is less than 20. Define the dummy variable high EL is equal to 1 if the percent of students learning English is greater than or equal to 10 and 0 if the percent of students learning English is less than 10. We run this regression and find that predicted test score is 664.1 minus 18.2 times high EL minus 1.9 times high STR minus 3.5 times this interaction term that we have defined. We have generated a new variable, high STR times high EL. The effect of high STR when high EL is 0 is negative 1.9. That comes from here, and if high EL is 0, then the second term and the fourth term drop out. The effect of high STR when high EL is 1 is negative 1.9 minus 3.5 because the fourth term is now in play. High STR is equal to 1, high EL is equal to 1, so we have this fourth term. It's negative 1.9 minus 3.5, it's negative 5.4. So class size reduction is estimated to have a bigger effect when the percent of English learners is large. However, the interaction is not statistically significant. If you see that the test statistic is 3.5 divided by 3.1, that's not going to be larger than 1.96. That's just bigger than 1. Now recall that we want to look at all of the cases. So we have this regression that we just saw in the last slide. In the table below, we have all of the cases. We have low STR, high STR, low EL, high EL. So low STR, this is high STR equals 0. High STR, this is high STR equals 1. Low EL, this is high EL equals 0. High EL, this is high EL equals 1. So let's relate these coefficients in this regression. Get that a nice big rainbow star. The coefficients in this regression to the table below, which has been tabulated by the different groups. Let's go by the table. Looking at the table, let's begin with the top left-hand corner, where high STR is equal to 0, high EL is equal to 0. So the second term drops out, high EL is equal to 0. Third term drops out because high STR is equal to 0. Fourth term drops out because both of these are equal to 0, and so all we are left with is the intercept, which is 600, the constant, which is 664.1. So for the low STR, low EL groups, the average predicted test score is 664.1. Now let's look at the case for high STR but low EL. So high STR equals 1. The second term is still equal to 0. This drops out. But high STR is equal to 1. So the third term, we have the third term. The fourth term is equal to 0 because recall that high EL is equal to 0. So the fourth term is equal to 0. And the second term is equal to 0. We have the first and the third term. So we have 664.1 minus 1.9 gives us 662.2. Now let's look at the lower left hand box. High STR equals 0. High EL equals 1. So low STR but high EL. In the regression, the second term, high EL equals 1. We have that one. The third term, high STR, that equals 0. So we don't have the third term. That third term is equal to 0. And the fourth term, high STR is equal to 0. We don't have the fourth term. So we only have the first term and the second term. 664.1 minus 18.2 gives us 645.9. Finally, let's look at the case where high STR and high EL both equal to 1. We have all of the terms. 664.1 minus 18.2 minus 1.9 minus 3.5. Folks, students, that gives us 640.5. This sums up our discussion of interaction terms when we have interactions between dummy variables. In the videos that we will discuss in the videos that come next, we're going to discuss interaction terms when we have some continuous variable.